My name is Przemek, you can call me like this, and this is joint work with, with Michał and Bernardo. It's on this Datalog MTL, so a temporal extension of Datalog, and we studied this language already for several years. It seems like it's very useful for things like stream reasoning or query answering, and we know that computational complexity-wise, it's very bad because it's X space, P space in data, and we already try to implement some reasoning algorithms, but it turns out that they are quite inefficient in practice. So while looking for some ways to obtain this more efficient in practice algorithms, in this paper, we suggest considering finitely materializable programs. So programs which in which reasoning can be done purely by materialization, which is not the case in full Datalog MTL. And our main results there are that we've shown a procedure how to decide if a program is finitely materializable in exp time. We also showed a sufficient condition which can be checked much easier in CoNP or in NL. And also we showed that reasoning in this finitely materializable programs is easier than in general. It's exp time complete, so it's actually no harder than pure Datalog. So the setting is that we want to perform reasoning on top of two components, dataset and the program. So the first component is a dataset. It looks like this. Datalog facts, however, each fact, for example, that device 13 has high temperature, is stamped with an interval of a rational timeline. So we consider the rational timeline. For example, this fact says that it holds continuously from 12.3 up to 36.1. We can also have facts which hold in single time points, of course. And then we've got a program, which is a second component. It looks like a Datalog program. However, now we can use this temporal operator. So box minus everywhere in the past, box plus always in the future, diamond minus somewhere in the past, diamond plus somewhere in the future, since and until. This is what you can have in a body. In the head, you can have only boxes. And each of these operators can be indexed with an arbitrary interval, giving this temporal metric component. So, for example, we can say that if this is the case, that always in the past, between -0 up to -15.5 seconds with respect to the current time point, the temperature of some X was high, then you should cool it. And the second rule says that if somewhere in the past 30, say, seconds, X was cool and now temperature of X is moderate, then you should cool this X. And then the main reasoning task is to check if a program and dataset are consistent, or if program and the dataset entail some fact. Actually, these problems are interreducible. And so, as in pure Datalog, we know that each program and each dataset have a single list model called Canonical Interpretation. So it contains exactly all the facts which are entailed by a program and dataset. And we can construct it by materialization, by forward chaining. Let me give you an example. We can take dataset and program I showed you before. So in step 0 of this construction, we have facts that come from dataset only. But then we can observe that we can apply this first rule of a program, and this in step 1 allows us to derive cool of device 13 in this interval presented in the picture. But then it allows us to apply the second rule. And if we apply the second rule, we obtain in the second step of this construction cool of device 13 is 61.3. And then we can observe that no more rules can be applied, a fixed point is obtained. And so this is our canonical interpretation. However, unlike in Datalog, this procedure can take infinitely many steps. And here's an example. We can say in dataset that even holds in 0, and then we've got two rules. The first rule says that if even holds now, then odd holds in the next time point. So in the first step of materialization, we can derive odd in 1. Then we've got a second rule, which says that if odd holds now, even holds in the next time point. So we can derive in the second step even at 2. Then we can once more apply the first rule to have odd at 3. And you can see that this procedure will take omega number of steps, so infinitely many steps. It does not terminate. So quite naturally emerging question is, which programs have this property that the materialization takes only a finite number of steps. And we call them finitely materializable. In particular, it means that for any data sets, materialization of such a program takes finite number of steps. And this class seems quite interesting because it allows us to perform reasoning just by pure naive materialization. As we will show, it actually leads to lower, but at least computational complexity, and also can be useful in practice. So the main two questions that we will answer now is how to determine, how to check if a program is finitely materializable, which is not that easy, and then also how hard is reasoning in these programs. To answer the first question, remember that we need to check if a given program pi finitely materializes for any data set. But here what we define is a critical data set. So we could think of it as a worst instance data set for a given program, which is a collection of facts, all the possible facts of this form, where P is any predicate from a program, S is any tuple of constants from a program, and this interval which occurs in this fact is of length depending only on the program. And the idea is that this interval is long enough to be a critical data set. And the theorem that we showed is that to check if a program is finitely materializable, this is theorem 1, it's sufficient just to check if program with this critical data set takes finitely many steps for materialization. So it somehow shows that indeed this is a critical data set. And the main challenge was here to show that this interval is actually occurring in a critical data set big enough to guarantee this property. Then we used this result to show how to check finite materializability in exp time. And our procedure just constructs a critical data set for our program and then starts materializing. We show that there is exponential bound such that if this bound on the number of steps of materialization is reached, it means that materialization will take infinite number of steps. So in our procedure, we start materializing, and then if a fixed point is reached, then it means that program is finitely materializable. Otherwise, if we reach this exponential bound, it means that program is not finitely materializable. But then also we showed that there is an interesting sufficient condition which can be checked much easier. And for this, we defined MTL acyclic programs. So for this, we constructed a dependency graph of a program, but now the edges of this graph are additionally labeled with intervals coming from a program operators. And then we say that program is MTL acyclic if it does not have a cycle on which the sum of intervals does not sum to 0. So this is much weaker, let's say, notion than acyclicity, but we show that this is sufficient to program to be finitely materializable. And this condition can be checked. This is theorem 4 in CoNP. And if program is forward propagating or backwards propagating information only, we can show that the check is in n-log space. It, in essence, needs just some graph reachability. And also we need to look at this number. So the complexity is a little bit higher than NL in general, it's CoNP. All right, and then the second question was the computational complexity of reasoning. So we showed that this is exp time complete in finitely materializable programs. And for this, we, in some sense, reuse this exponential bound that we already introduced. But what is maybe interesting to observe there is that, first of all, these finitely materializable programs are easier than in general because we have this drop from exp space to exp time. But on the other hand, remember that exp time is the computational complexity of pure datalog. So what we obtain there is a class of programs which allow you to perform non-trivial temporal reasoning and which extends all the datalog programs. So finitely materializable programs contain all the datalog programs. But we can do this without any price in terms of computational complexity. It's for free because the complexity is the same as in pure datalog. This is why we believe that this class is quite interesting. So to conclude, we introduced this class of finitely materializable datalog MTL programs. which allow you to perform reasoning just by pure materialization, which can be very scalable. And we showed how to check membership of a program to this class and some sufficient condition which can be checked easier. And also showed that reasoning in this class is as hard as in pure Datalog. However, this class contains all the Datalog programs. And in future, we plan to study data complexity. We believe that it's also the same as in pure Datalog. However, it's not that easy to obtain upper bound for data complexity. And the second thing, we would like to implement and test our reasoning mechanisms, especially in some real applications, to see how they work in practice. So thank you very much for attention, and I'm of course happy to discuss now or during the poster session if you have any more comments and questions. Thank you.